Okay, so I think we should not let people who joined on time wait for people who have not joined on time. So let's just get started, and let's see who joins. People who join, let them join in as we go along. So thanks a lot for joining today's webcast. We've been running this series, a 5-part series on Industry 4.0 and how you can actually drive Industry 4.0 conversation within your organization. We started off with the first session, which was setting the context in terms of what is Industry 4.0, why is it important, and what are some of the things that you should consider when it comes to Industry 4.0. We then had a session around intelligent asset management. We did that with Malaki. Actually took us through what can be done from an intelligent asset management perspective. Today, we move to the next phase of the conversation, which is around intelligent products, intelligent and connected products, why this is important, and how organizations can actually drive significant amount of value by developing and creating new connected and intelligent products, which you can then deploy as new business models as well. So we have with us the product team, Ankit Agarwal, Ayan Pandey, and Saurabh joining us on the call. They'll take us through about 45-50 minutes into the session around take us through some examples and also talk to us about how SAP can actually enable customers to build intelligent products. So with that, maybe I'll invite Vipin if you have a couple of words to kind of share, and then hand it over to Ankit and team for them to take us through the content.
Thanks, Mukesh. This is the brave new world, and within this world, with technology changing so fast, it is imperative on us for our survival, for our competitive edge, that we follow these new age technologies. We follow as much capability that Industry 4.0 or Industry 4.0, whatever you might call it, brings to the table, and reach out to sort of going beyond what we are normally used to be doing. And these are technologies available, being used. And so the question is, why should we do it? The question is more, when do we do it? And that is where we are trying to drive this conversation towards. Over to the team to take you through that entire process or entire set of capabilities that Industry 4.0 brings to the table.
Thank you, Vipin. So hi everyone, and good morning, good afternoon, and good evening if you're based out of New Zealand. So yeah. So my name is Saurabh. I'm part of the SAP Enterprise Product Development team. And today, as a part of this session, we will talk about what are intelligent products and how SAP can help you or your organization make your products smarter and build and design intelligent products. Ankit, if you can move to the next slide, please. So as a part of this agenda, we will touch upon what is an intelligent product, right? And then we will jump directly into some of the customer examples or the customer use cases that we have recently worked on. Then we will touch upon the technology, how to build intelligent products. We will have some information on the pricing, and the last session is the last part is about the Q&A. Yeah, the next slide, please. Okay. So what is an intelligent product? According to us, intelligent products basically rely on 4 key pillars or the 4 key aspects. The first is the technology, which we say, okay, whether it's the sensors, it's the processes or the softwares that actually lets you even get that information, right? And then once you have that in place, it's the intelligence, that is the access to that data to drive meaningful insights based on the way the product is either used or product functions or performs. So you then kind of experience that. So that these are the experiences. And then once you have that information, right, this data is then fed back either to the R&D for the product's improvements, or from the operations again back to the OEMs, right, to ensure the product reliability and ensure that you decrease the downtime. So more on the operations and the feedback mechanism. Next slide, please, if I want to come to that. Yeah. So overall, if we look at, okay, the key requirement to designing any intelligent product is via digital thread. What do we mean by a digital thread is right from the moment, if I look at it, right from the designing, if I go to the left side, right, you have, right, when you conceptualize that product, right, you have that information, and that information flows to the build phase, then to the install phase, and to the operate phase. And it not only stops there, but that information is again fed back. And this is what we want to convey with talking about the digital thread. And this is what we are working on right now as a part of our product portfolio. And yeah, so this will really help you. So if we go to the next slide, Ankit, please. To say it in a simplified terms, right, what we are talking about is if you want to capture the value at stake and you want to design an end-to-end, you need to design an end-to-end digital thread, right? So the product teams, they get the information from the, when they design the products, they feed the digital thread to a digital product model, which we call as the digital thread, which is then consumed by the extended enterprise, which are your customers or their consumers. And then there we have how the customer actually uses that product. We get that information from the operations, and this information is then fed back. So there is a feedback mechanism, right, which is then consumed by the product team, right? To kind of, so this is a kind of a, I would say, a loop mechanism that goes on. And this is how you build and design those digital products or the intelligent products. The next slide, please. Okay, in order to design the intelligent products, right, what are the topmost priorities for the organization? We talk about the top line, the bottom line, and now the most happening word is the green line, right? So when we talk about the top line, right, how do you define new products, right? How do you create new business models, right? When we look at the bottom line, I'm just taking some of these, I would say, tiles from there, but there are a lot of other things you can do, whether it's lowering the product cost, right, lowering the life cycle cost, or when we talk about decarbonizing the products, right, how do you reduce that? How do I increase the reliability so that I don't over service or under service my assets and reduce those downtimes, right? So this is, I would say, it's more about the intelligent products. Now we want to talk about the customer examples, and then we will come back to the technologies that will enable you to build those intelligent products. So over to you, Ankit, for the examples.
Thank you, Saurabh. Before I start, colleagues, few words about myself. My name is Ankit Agarwal. I'm based out of Norway. I am part of the same team as Saurabh. So basically, we are part of a PLM cloud solution, and within our solution, we have capabilities to support intelligent products from the OEM side. So even if you are equipment manufacturer or if you're operator. So, and how our customer have done that in the past, I will walk you through some of the customer use cases. So we have both OEMs who are leveraging digital twin and digital products technology to enable new business model. And we have also a lot of operators who are monitoring their assets based on virtual sensors and digital twin with our technology. So going into the customer use cases, so I will start a customer use case from the utility industry. So it's from so I cannot name the customer as they are not our reference customer yet. So it's for so this project was done for a utility company based out of France, but the specific project was done for a plant that they own in Latin America. And it was so the target of the company is to basically increase their share in the renewable energy sector. So traditionally they've been they are quite big in nuclear, natural gas and petroleum, but now they want to focus more and more on PV technology, and also in future extend it to wind energy. So and for this specific project we focused on the PV plant. So typically what happens in the utility industry, specifically for PV plant, is that at the end of every quarter, you need to send your colleagues or your maintenance engineers to inspect that if anything is wrong. That's the first aspect. And second aspect is to clean the panels. So as efficiency of PV panels is highly dependent on how clean they are. And traditionally most of the maintenance activities are based on the time schedules inspections, right? So but without technology they wanted to see if they can switch to health based maintenance. And the reason to do that was first of all, most of these PV plants are located in quite remote location, so it's challenging to send inspection engineers. And imagine if, so for instance, for this PV plant, it was not a huge power, huge plant. It was relatively quite small for a PV plant. It was 2 megawatts. Even though it was 2 megawatts, still there were around 9,000 panels in the whole plant. And on top of that, they had also around 2,000 to 3,000 fuses, which were installed in that specific PV plant. So even though when they sent the inspection engineers, it was almost impossible to determine which fuse has broken up, because otherwise they need to manually inspect so many fuses, and that is basically an impossible task for them, or very time consuming task for them. And also you cannot install so many sensors, because every sensor is quite expensive, and then you need to spend time on the maintenance of that specific sensor. So they were looking into a technology that using the information of the existing sensors, can we give them outputs, or let's say produce virtual sensor data which can give them refined information on what has gone wrong. For instance, which fuse has been broken at which specific location, and also when do they need to do any maintenance. So basically answer all 4 W's, what we call it. So what occurred, why it occurred, when it occurred, and where it occurred. So and this is how this is very high level flowchart, how it looked like. So they are our SAP's S/4HANA plant maintenance user, but this technology also work with, if you are also on older ERP system, for instance, if you are on ECC also, that would also work. So that's not a problem. So in this PV plant, they had IoT sensor data installed, for instance, for temperature, for irradiance, for voltage, and they had also current and power values which they were actually producing only on a few locations. So in total, this overall IoT sensor data values which they had was about 8. So then what we did, we used that input, this IoT sensor data available as of today on the plant in what we call a simulation-based digital twin. And you could imagine a digital twin, basically a replica of your asset. So this could be a very refined, FEM-based or CAD models, etc. Or it could also be as simple as a Python script, really depending on the use case. So for this specific use case, we focused on a 1D model. So no CAD models, no refined finite element models, a very simple component-based model. So where you can just use the sketch of the plant, how different components are clubbed together, and then you produce a digital twin of that. So that was used as the input. Then as an output, we produce a multiple sensor data at multiple locations that also included current and power at different locations. So now we were able to produce for in total around 40 to 50 additional virtual sensor data. So now customer has in total 50 to 60 time series data that they can further use to do anomaly detection. Because if they're directly going through this loop, then first of all, you will never know what should be your actual performance and what you're actually producing. So with this technology, you can also determine what you should be actually producing, what should be your best performance, and what your actual performance is, right? And that's one aspect. And second aspect is if you are not, because if you're doing directly anomaly detection based on machine learning, then you need a lot of data. And typically when you talk about these kind of assets, you always struggle with getting good data, because simply either you need to install a lot of sensors, or simply historic data is not available, or asset is too complex that you cannot obtain the sensor data. So on those cases, you can always get it via virtual sensor, via digital twins. So then only by installing 8 to 10 physical sensors, you still have around 50 to 60 virtual sensor data that can be further used in anomaly detection in machine learning. And once you have an anomaly, it could be based on if a fuse has been broken, or if you need cleaning of the panels, or if you are producing less outputs than you should be producing. It could be any of the anomalies. And then whenever any of these anomalies detected, then you would get an alert in your backend plant maintenance system with very refined information. For instance, if a fuse has been broken, that this specific fuse at this specific location has been broken, and this is how it's impacting the performance of your plant. And so this is why you should take some action. So then as a plant operator, you can define your limits that, if your performance is below than this value, then you will send your maintenance engineers. So then you actually know when to do maintenance and where to do maintenance. Instead of doing a typical time-based maintenance, you can switch to what we call intelligent maintenance, or digital twin-based maintenance. So this was the first use case. So technology used a high level, if I may say it, were used IoT, machine learning, and digital twins. Then again, a second use case from the renewable industry as well. So here it's for a wind turbine monitoring. It was done for a utility company based out of Norway. So here again, a similar use case. They wanted to again switch or look into if they can do sort of smart and intelligent maintenance over traditional time-based maintenance. So first aspect was looking at the performance of wind turbine, and second aspect was maximizing the asset life and minimizing the operational costs. And typically what happens is that whenever they have these maintenance cycles in order to do maintenance in their wind tower, so then they will shut down their operations and they will manually climb down this wind tower and check all the locations in the tower where there are issues with concern, for instance, with high structural fatigue, with high vibration, etc. And this is of course a very time consuming process. It also takes a lot of money because because you need very refined equipments, etc. And also you need to, also logistic costs. But then they use a lot of time as well because they don't know where to actually inspect, so they inspect everything. So use case was that they wanted to see if they can see when to do maintenance and where to do maintenance, right? So if I go to next slide. So now so there were different use cases. For instance, as I mentioned, for the previous PV plant case, we focused on the component based, where you don't need any 3D models or CAD models. But in this use case, customer was interested in specific sections or very refined information of the wind turbine. So we used an FEM based approach, finite element based approach via CAD model. So then once we ran simulations, we were able to pinpoint, for instance, on which specific section you need to do maintenance. For instance, now we know from simulation that it's these specific sections marked in the red, we have their relatively higher value of damage, or what we call in structural engineering terms, structural fatigue. So this is where you need to do some maintenance. But for instance, the parts or sections lower than this, the value of the damage is relatively low. So then they don't need to spend time in inspecting here. So then they can directly go up here and then fix only this specific aspect. So, and this was first aspect, and second aspect was, of course, the performance. If anyone is from utility industry background, you might know that in wind energy sector especially, there's a problem with the EO misalignment. So this is basically when your wind turbines are not aligned with the wind direction. So bigger the difference between the alignment of the wind turbine, or what we call rotor, with wind direction, the lower the performance. So, and in order to avoid that, typically there are control systems on place in wind turbine which can follow the wind direction as much as possible. So they also wanted to see if their control system was good enough. So were they able to follow the wind direction as much as they should be following? So then that was aspect of the performance. So then we gave them very good suggestions via our system, or let's say rather system gave them an automatic suggestions that these are the improvements you need in the system. And after implementing those improvements, they were able to increase their performance by 15 to 20%, and that's very big value for a wind turbine operator, for one wind turbine. Okay, the next case. So now first I started with utility use cases. So then now I'm talking about a public infrastructure use cases. So here, again, it's a bridge that we are monitoring based out of Norway. It's a really old bridge, and it's as you might know, Norway, the terrain of Norway is quite mountainous, right? So the structures there are usually a bit complex, and this bridge is 80 years old. So now the traffic load on this bridge is more than twice of what it was designed for. So that's first aspect, and second aspect is that it is really old, and the location where it's located, this is the only way to connect to two parts of Norway, northern Norway and southern Norway. So for instance, if something goes wrong here, then there's a big issue of logistics. So then you will then basically the whole transportation between northern Norway and southern Norway will crash. So and you cannot overnight replace this bridge. So then they wanted to see if they can monitor the performance or the integrity of this bridge in the real time. And then we helped them do it, and this was done again via digital twin. So basically we suggested customers to install some IoT sensors. So in total they installed 5 IoT sensors in the span of the bridge, and then we use that IoT sensor in our system to produce virtual sensor information on, for instance, structural fatigue or damage, similar to wind turbine case. So on a FEM model, for instance, where exactly vibration is happening, what is the structural fatigue in the real time when so many trucks are passing, etc., parameters like that. And actually, a very interesting case happened a couple of months ago, that one part in one of the piers broke, and so actually that specific pier started vibrating, and as soon as the vibration happened, system immediately detected it and gave notification to the maintenance and operation engineer that this specific pier has much higher value of damage, and then they went to site right away within next hour, and then they saw it actually it was that actually something was really wrong. So then they immediately closed the traffic and did the right maintenance. But imagine if this did not happen, this could really lead to a very big catastrophe. So this was a really good really good use case. And also if you can if you're more interested in what this specific use case, we also have a YouTube video available where customer talks about how exactly they benefited from the solution. So when we share the deck, we can also share that YouTube video link. So please feel free to watch that video, and customer customer had really talked about in detail about this specific use case. Okay, and then now we go to a case. So as you can see, as I'll talk about different use cases, that our use cases are not, and not limited to any industry. So we have almost use cases from each and every industry. I will show some of them today, but I can say that we have use cases, for instance, from utility, from public sector / transportation. Then we have use cases from marine industries. For instance, this is floating fish farm. And then we have use cases from oil and gas. We have use cases from life sciences. Really, yeah, almost each and every aspect of the industry. So coming back to this specific use case, so this is from a fish farming use case. So basically, this is also based out of Norway. We are monitoring a floating fish farm, and this is the second biggest floating fish farm of the world. And since whenever we talk about floating structures, it's always much more complicated to do maintenance and to inspect to do real-time monitoring of those assets. And in Norway, they have really high regulatory demands on the fish feed. So basically, the waste which fish produce, that how do you manage that? It should not be released into the water right away, because then it spoils the quality of the water. So that's a requirement by the authorities. So they wanted to, first of all, of course, look at the structural aspects. For instance, the integrity of the asset, and during high sea conditions, for instance, how it's impacting the vessel shape, what are the failure modes it might produce, etc. And second aspect was, of course, that how do you manage that fish feed, what we call it. So the fish waste. So how much fish they produce and how it's recycled, etc. And then third aspect, that if during critical conditions, if there is some issue, then they cannot again install sensors everywhere. First of all, it's floating, so it's installing sensor, doing anything basically, it leads to really big costs, because you need to drive all the way into the ocean, and then doing any sort of downtime or any sort of maintenance activity is highly costly. So then if you can do health-based maintenance, then you only do maintenance when it's required, instead of just following your maintenance cycle. And also, when you do maintenance, you can actually pinpoint that which specific joint in this structure, or which specific location in this structure requires maintenance. So then you can do what we call key or very spot focused maintenance. So that was another aspect of this use case. And after our meeting, if any of you is interested in any specific use case and wish to have a deep dive session, I will be happy to help you there. So then we can have one-to-one later on. So today I will not talk about in very deep dive. It is more like to show you what kind of use cases we have from the industry and how it can be used. So now this is the use case from steel industry. So in the steel industry, they typically use a lot of cranes of different criticality, of different size. And typically, imagine if you are a train operator, or a steel manufacturing company, then you are using cranes from different OEMs. And typically, as you would see that different OEMs also come with their own sort of, let's say, monitoring solution. But if you're an operator, you are using different OEMs for different cranes, and then you might have 100 different systems to do monitoring. So then as an operator, it could be really challenging to keep track of all different assets. So then this specific customer was looking at one platform, basically, where they could monitor all of their assets, irrespective of whichever OEMs they're coming from, where they can do all the sensor data collection, all the digital twin related data processing, all the notification handling. And then that was one aspect. And second aspect was that in the cranes, main part of maintenance is the lubrication of the joints. And then again, similar to other industries, that was done for over time. So for instance, once in every few months, but sometimes they realized actually they did not need to do lubrication. So in a way, they were over maintaining their assets. So then they wanted to, optimize that. So then we were, if I go in a bit more detail here, and then we were able to give them very refined information on when to do lubrication and when to and where to do lubrication. So then again, they can switch to health-based maintenance over time-based maintenance. So again, a similar flow to, for instance, the PV case. So we have a crane here, and on that crane you have few IoT sensor streams. So in total, they had 6, if I remember correctly. So crane position, trolley position, hoisting position, weight, cable weight, etc. So then these were used as input to our simulation-based digital twin. And then out of that digital twin, we produced information via virtual sensor data on hoisting parameters, lubrication time, forces at different locations of, or let's say different joints of that specific crane. And then that was fed as input to train machine learning algorithms. And then whenever they required maintenance, they would get an alert into their backend system that now is the time that you need to do lubrication on your point, on your crane at this specific point. And then all of this was so this, I'm showing this flowchart for one crane, and then they can use the same technology or same platform to extend it to their other assets. So then they get a one scalable platform where they are doing the operation, or let's say monitoring for all their assets, instead of going into 100 different solutions from 100 different OEMs. And then this is example of, so this is an ongoing pilot project. This is for an autonomous tractor. So they have installed three sensors, 3 IoT sensors, and based on that, they are doing. It's quite similar to the use case from the previous IMNC industry. So the previous crane use case, basically. So here they are also looking into the maintenance aspects from the structural perspective. So which are the locations where you have high value of structural fatigue, when you need to do maintenance, etc. So this is quite a small company which we are taking a pilot project for, but it's very interesting use case since it's totally autonomous. And if everything is successful, then the customer plans to deploy it to their all of their tractor asset. So then this way, they don't need to worry about any maintenance activity. So whenever there's a maintenance need, they will, or let's say customer will get a notification in their system that now is the time to do maintenance at this specific location. So this was really good example of how intelligent product can really support totally automated process. Now there's no, if we're talking about autonomous vehicle, we are talking about very like intelligent maintenance strategies. So yeah, this was very interesting use case. And so now most of the use cases so far I have talked about, from a very operator perspective, that if you are operator, how can you use the intelligent products technology or in order to do your intelligent maintenance. So now there's initially, as I mentioned before I started, that we also have OEM who are even leveraging new business model within this technology. And this is a very good example of that. So now it's an OEM, which is typically, so their traditional business is manufacturing of progressive cavity pumps. To those who don't know, so cavity pumps are typically used in oil and gas industry, and they operate at really high depths, and then there is no way that you can monitor the health of their pump at these larger locations. So then, as an operator or as customer of our OEM, as an OEM, if you have bought a pump from them, and now if you start operating for your operations as required, and then if you want to do operation, or if you want to do any maintenance, you need to stop your operations and you need to pull the pump out, and then you need to do some sort of maintenance. And again, typically most of the times you will realize that you don't need to do maintenance because you are simply over maintaining it. And if you could simply say that you could install IoT sensors here, but that is simply not possible because now we are talking about depths, a really high depth, where physically it's not possible to install IoT sensor as of today, right? So the only way to do the maintenance, traditional maintenance, is stopping your operation, pulling the pump out, and then inspecting if requires maintenance, and then doing the maintenance if required. But now with this new business model, now the OEM is enabling their customers, to actually monitor the health of their pump via virtual sensors. So now they don't need to stop their operation if maintenance is not required. So they can install virtual sensors via digital twin, and then so now as an OEM you have two business models. So you are selling a physical compressor, or physical pump, similar to before, but on top of that you're also selling, let's call it a digital product, or intelligent product, or digital twin, that is allowing your customers to do, or to monitor the asset at those locations where otherwise you were unable to do before. So now as an OEM you have also a new business stream, so where together with physical product you're also selling a digital product. So together you're selling, basically you could call it an intelligent product as an OEM. So basically in this project, what OEM did, so this was also again a pilot project, and now we are in discussion with OEM, where OEM has some customers interested, who are interested in this virtual sensor based technology. So for this specific pilot project, and these were the sensor data available, and these were current voltage, drill head pressure, etc. And then we used this information in a digital twin. This was a 3D advanced digital twin, something similar to this. And then as an operator, they're able to produce these sort of parameters at those locations, really deep locations that we're talking about. So for instance, fluid level, pressure, torque, temperature, wear and tear of rotor and stator, and really all the parameters that you need to do condition-based monitoring of that specific cavity pump, which is operating at these really high depths. So now as an operator, you don't need to first of all do any downtime, just to make sure your asset is working well, or your pump is rather working well. You will only stop the operations when you will get a notifications from the system that this is what you need to do, and this is what something going wrong, right? Without any physical sensors at those locations. So it's sort of a win-win for both OEM and operator. So for OEM, you are enabling new business model by also selling your digital twin, and as operator, you are using the digital twin in order to do condition-based monitoring over time-based monitoring, minimizing your maintenance costs and minimizing your downtime. Okay, and then there will be one last use case that I will quickly talk about, is in the EV space. So it was done for a vehicle manufacturer. This is basically battery health monitoring. And so this is for example of a battery from a vehicle, and then we have some physical sensors which were passed down to input as a digital twin, something like this. In EPD, this is specific product that I'll take it in the next step. Let's say for now as in SAP solutions, intelligent solutions, and then we were able to produce virtual sensor data on the remaining lifetime of the battery. What is the state of health? Temperatures at different locations in the battery, health, wear rate. So in the battery, as you know, it is impossible to calculate the aging of the battery via physical sensor. It's just simply not possible, right? And also from the other use cases as well. There are some parameters, even though if you install IoT sensor, you cannot measure them. For instance, structural fatigue, as I showed you from some of the use cases, right? That you cannot never measure by physical sensors, or for instance, this aging of your equipments, that also you can never measure. So yeah, so on this kind of use cases where these kind of parameters are important, for instance, aging of your asset. And now when I talk about asset, you could think of any complex asset. It could be also for instance, compressors, it could be transformers, it could be really any asset. We also have other use cases, but since we don't have enough time today, so we'll focus on these use cases, and then if you're interested, please reach out to me, and then we take it I can show them to you later. Okay, coming back to the topic. So now to this battery use case, so we for instance have these physical sensors, so that is measuring state of charge, what is charging and discharging power, and what is the temperature at one specific location. And then by using that information, we are able to get the virtual sensor information for the other parameters. For example, the state of health wear rate, and what is the energy use, etc. So if we take a full cycle, so then there is a e-scooter where battery is fully charged. It's and then now battery is discharged, right? And now it means that you got a notification that you need to charge the battery. Then you start charging the battery, and then battery is fully charged again, right? And so this is one full cycle of the battery. And now the charging and discharging of your battery is measured by the sensors installed in the battery. That is nothing new, right? This is typically we have in every battery. So for instance, this is charging, and now here is fully charged. Now we use this information to calculate these parameters, right? So how your state of health of battery is changing with every charging cycle of your battery. So basically the decrease in the state of health. And again, these kind of parameters you cannot measure only by having physical sensors. You need to calculate them. And you can calculate them via digital twin, via virtual sensor, and then also, of course, then this is the decrease in the state of health when fully charged. And then we also show some energy used. And then this is first aspect, of course, looking at the aging of the battery. Another aspect, if you are OEM, you could think of reducing the number of physical sensors that you need on battery, thereby reducing the weight. As an as a battery manufacturer, there is a lot of focus on making efficient batteries by having a lightweight battery as much as possible. So reducing the amount of physical sensors installed on that battery is one of the way to do that. So you can just install minimum number of physical sensors on the battery, and then use that information to calculate other parameters via virtual sensors, which requires no hardware. It's totally software based. Yeah, and then as said, they are looking at different parameters. For instance, battery aging, battery temperature, then also efficiency, etc. And then also in some cases performance as well for some of the batteries. Yeah. Okay. So then I talked about all the use cases, and I think we are almost by the time. So I'll quickly walk you through the product. So I talked really about digital twin, right? And what exactly is a digital twin in our sense? So you could think this of a physical asset, and on your screen is a digital replica of your physical assets. And now in this asset you have if I pause this video for now, we have this one IoT sensor that is measuring the movement in this specific cantilever beam, and this measurements is given as a feedback to this specific digital twin or digital replica, and then it runs multi-physics simulations in the real time and gives you outputs, for instance, for parameters like structural fatigue, structural stress, strain, depending on the use case, it could be anything. And now you can generate these values as what we call it as virtual sensor data. So to summarize, you have physical asset, you have digital twin or digital replica, then you have one physical sensor, and then digital twin uses that physical sensor to calculate virtual sensor information at different locations for different parameters of interest. Yeah, and then this capability, right, which we talk about, these intelligent products, and for different OEM models, for different operator models from different industries, all the different use cases, they have been covered with our SAP product, what we call it as an enterprise product development. So the goal of this specific solution is to cover all three phases of your product, starting from define, develop, and deliver. And when you talk about define phase, typically you would start with the design. So now, for now, let's think, I'm talking about perspective from an OEM for now, and then I will switch to operator perspective. But let's for now focus on OEM. So as an OEM, when you are designing a product, you start with, first of all, what are the requirements which are coming, right? So requirements could come from your market insights, from your customers. It could come from your research units. So there could be different requirements, right? So then you would prioritize the needs and requirements in a specific, what we call it as a requirements engineering, because someone might just say that, okay, I need this, right? But how do you achieve this? Then you need to break down that specific high level requirement into smaller requirements, and this is what we call requirements engineering. So that is what we call it as a define phase. And then once you have your requirements clearly defined, then you would go into develop phase. And then during the develop, or you could call it manufacture phase, you have to collaborate with different parties. It could be collaboration with your suppliers, it could be collaboration within your party, or it could be compliance requirements. For instance, if you're talking about process industry, chemical or pharma industry, there are compliance requirements, formulation requirements. So all of these kind of requirements which you need to take into account during the develop phase. This is what you can do in the develop phase. And then finally, once you have developed your product or manufactured your product, then you would deliver it. And then as said, as OEM, you can also generate a new business stream. So instead of just delivering traditionally your product, you can also deliver let's say a digital twin based service as well. So now you can also sell for a digital product. So if we go into a bit more detail of each and every of these 3 Ds which I talked about. So first of all, I talked about the requirements part. So that requirements could come from voice of customer. Again, we have our solution with, so it could work with if customer has their own solution to get feedback, so we can help with integrations. Or if they don't have it, we also have our own solution that can help in getting the voice of customer. And then once you have that all the requirements, then you can do it in sort of break them down in what we call it requirement engineering. And then once you have those requirements, then you would go into the develop phase. And now in the develop phase, for instance, let's take example of a crane. So in a crane, there are different types of systems. So there are structural system that you need to design. There is electrical systems that you need to design, right? So there are different systems you need to design first. And all that system can be covered in one of the business process within our product, what we call it as system engineering. And then during the development phase, you need to do collaboration between different groups in your units, or you need to do supplier collaboration, or you need to do collaboration on the specification, that what are the specifications you need to have in the product. Or if you talk about a process industry, then there's also product validation that is quite relevant for the process industry. And then you might have to do collaboration on different type of documents and different data. So all of this can be handled in the development phase. And then there's another aspect is digital twin. So this goes into direction of what we talk about in the new business streams, right? So anyway, typically when you're designing and developing your any physical product, right, you always have you have always done R&D of that product, right? So these kind of simulation models that I talked about earlier, right? This digital twin, digital replica of your asset would already exist in your team. So now it's only about monetizing on it. So now you can, so you already have that digital twin. but then you can sell that digital twin as a service in the deliver phase that I'll talk about later. And then we also have other two business process coming up. So now this intelligent handover is already has come up in Q2, and then we will have another one coming out, intelligent routing. So basically, intelligent handovers deals with a conversion from engineering BOM to manufacturing BOM. Yeah, and then once you have delivered your product, right, you can establish collaboration with your operators, with your customers. This business model could look different depending on what operator and OEMs are comfortable with. One example as an OEM could be you take responsibility for all the service. So for instance, you ask your operator to share OT data back with you, and then based on the OT data that you are producing, you can monitor the asset based on the digital twin. That's one business model. And second business model is you are selling the digital twin, for instance, for that specific cavity pump use case that I talked about. Then operator themselves take care of the maintenance activity based on the digital twin. So this, if they don't want to share the OT data back with the OEM. So as an OEM, you have two different choices, right? So this is how you can think of your digital products, or how do you want to collaborate with your customers on digital products. So you're basically monetizing on the R&D models that you already have, that you are never using in maintenance and operation, right? And then also we have support for visual services and support and spares, visual work instruction, etc. Okay, so now since we are over time, so I will skip this part. Maybe yeah. So then I will talk about. I'll skip these parts. I'll talk about maybe this specific use case. So this is one of the business process that I had explained earlier, right? So now as an OEM, right, you could also leverage product as a service use case. For example, let's say instead of selling any asset, you could, so we also even have customers who are doing it. So we have a customer who is actually selling not the compressed airs, compressors, but compressed airs as a service. That's one. So you are basically delivering and you're basically delivering product as a service. First use case, and second use case is quite also is becoming common in the IMNC industries from the cranes. So as cranes are very expensive, right, to buy for operator, so then a lot of OEMs are actually sort of, let's say, renting out their crane. So and then their operators are paying them based on the per use and how they're using the asset. But in order to do that, OEM needs to monitor their asset in the real time, right? How exactly an operator is using your asset, because let's say, if you're not using the asset the right way, then of course the breakdown or the wear and tear of your asset will be much faster compared to how it should be used. So then as an OEM, in order to charge your operator in the right way, you need to do the real-time monitoring of your asset, and this can be leveraged by the digital twin. So as said, you can create new business model, and then your customers could pay based on the subscription, or you could be based on the pay-per-use models. You are monetizing on the engineering models that already exist in your backend. And then we have integration with what we call it subscription billing. So then with the subscription billing, you can automate the billing process in S/4HANA. And then asset user can provide you also feedback, and we enable the full this collaboration between OEM and operator via what we call it as asset intelligence network. So again, we can talk about that if you are interested in one-to-one. And also the other business process which I skipped for today, these ones we can also talk about that if something is interesting for you later on. And now that I talked from OEM perspective, now quickly talking about from an operator perspective. So I talked about different maintenance strategies, right? What operators were using earlier, and now they're switching to this what we call smart maintenance or prescriptive maintenance. So typically there are three types of maintenance strategies that and maintenance any operator would define. So one is very traditional, that is reactive. So that you do maintenance when something has broken down, but that of course comes at a high cost, right? It suddenly is a downtime. And also sometimes if you don't have the equipment or that specific part in your inventory, then suppliers might take advantage of your situation, right? Because then they can charge as much as they want. And in order to do that, either you would have a very large inventory, and then you would have large costs related to inventory in case of reactive failures. But then second aspect is proactive or time-based maintenance that I talked about. So you have planned your maintenance activities every few months, or depending on how you would like to do. And third aspect is what I talk about today. That is prescriptive maintenance. That is, you are doing maintenance based on the health of your asset. So meaning that you are actually doing maintenance when you need to do maintenance, right? And this can be done by different technologies, which I mentioned, right? So I showed some use cases where customer was using only simulations. For instance, the wind turbine case. Then there use case of PV panel and the crane use case where customer was using simulations and predictive technology. When I say predictive, I mean machine learning technology. So really so you can define your asset strategies based on, of course, how critical your asset is for your operation, how some downtime will impact your operation. So you can of course convert all this value directly to dollars, right, in order to do good value engineering case. And all of the customers which I mentioned earlier have saved a lot of money on their maintenance and operation activities without smart technology or without intelligent technology. And doing this kind of smart maintenance also allows you to do all sorts of this kind of analysis, right? Root cause analysis, meaning what has gone wrong, risk-based inspection, failure mode analysis, reliability centered maintenance, etc. So now if I, in ideal scenario, right, how let's say high level a business flow would look like. So for instance, now we have a temperatures, I'm talking about a very high level. So let's say we have a transformer, right, have a different temperature, different sensors installed on it. For instance, temperature, SCADA system, etc. Could be anything. So now we would read that data in our EPD solution, and then we would deploy the simulation models, or what we call digital twins, of that specific transformer on EPD system. And then you could get a virtual sensor information on the parameters you are interested in. For instance, could be thermal fatigue, could be structural fatigue, could be information on when you need to do the changing of oil of transformer, for example, right? Or it could be aging of transformer, or it could be any engineering KPI, basically, depending on what your asset is, what is the use case, etc. And once you have that information of those highly refined data or highly refined engineering KPIs, then you could use that information in machine learning based solution. That is what we call it as SAP APM, where you can do anomaly detection. And once you have alerts, then you could integrate it back to our SAP's backend EAM system or plant maintenance system, right? And once you have a maintenance request, it could be for instance, right, something, let's say oil needs to be changed. I'm just saying, for example, right? And then based on that, what kind of maintenance you need to do, you can trigger work order. So basically telling your maintenance engineers exactly on what kind of equipments they need to bring to site, because now you know what has gone wrong and where it has gone wrong, right? So you save a lot of time, because if you think about traditional perspective, so it could be that maintenance engineers went to the site, but they did not bring the right equipments because they did not know what is the root cause of the issue, right? So now you know what is the root cause of the issue, so your maintenance engineers will bring the right equipments the first time. And all of this can be managed by what we call is SAP's field service management. So it's not one solution, it's different solution, but together what you can enable the full end-to-end intelligence maintenance process. And specific this digital twin capabilities that I talk about, this define, deliver phase, that is covered within EPD, Enterprise Product Development. Okay, and now a short one slide on simply pricing, how it is based. So as I mentioned, our pricing is EPD is enterprise product development is not one solution. Rather, it's a suite of different solution. So, for instance, if you are interested in the define phase of the solution, or if you're interested in the collaboration aspect with different during your development phase, or you're interested in the visualization aspects, or you're interested in the digital twin aspect that I should talk about later, that is connected products. So all of these other aspects are based on how many users will have access to the system, and connected products is based on what we call device, or you could simply relate it to the asset. So for instance, one crane would be one asset. So how many assets you want to monitor, and then of course there are other parameters. For instance, because it's a cloud product, so it's based on the amount of data that you produce. So that how many IoT sensors are installed, how many how many virtual sensor will you produce, etc. So parameters like that. But if you want to try out different capabilities of EPD, you don't need to buy it separately. So you just need to buy on a single material code. So you could think of EPD as as tokens, right? So then you have bought a specific number of tokens, or and then tokens are basically capacity units. So let's say you have bought 900 capacity unit. Now as a customer, it is up to you how you want to distribute the capacity units or those tokens between different capabilities of EPD. So it's really flexible. It really does not matter what you use the boat capacity units for. Yes. Then thank you for having me. So if there are any Q&A and would like to have any discussion, I'll be happy to do that.
So we are now open for question and answers. What I would request is, if there are any questions, please put those in into your chat, or you can open up the mic and start speaking about it. Ankit, I have received where I'm asked whether this digital twin can be used in the product maintenance piece, predictive maintenance part of the product, and how is that going to happen?
Yes, absolutely. So if I quickly go back, so if I quickly go back to one of the use cases, right? Let me go to PV use case. I think that's easiest to explain. Let's take this one rather. That's also okay. So for instance, now, right? So now you are based on the digital twin, you're producing all these refined engineering parameters, right? So now you have simulation based digital twin that is producing the parameters that are going as an input to your machine learning engine, where all that anomaly detection and the prediction is happening. So when you talk about predictive maintenance piece, so this is where it's quite central component. So now, because when you really talk about prediction, it's simply based on machine learning, right? And machine learning is based on the amount of data you have. So if you don't have enough data, so then that prediction will not be accurate. You might generate a lot of false positives, right? And that's what you would like to avoid. And that's one aspect. And another aspect is, even if, let's say, you are able to generate an direct alert that okay, something has gone wrong, but then you will never know what has gone wrong and why it has gone wrong, right? But digital twin being a central component here, for instance, in this use case, right, it allows you to rectify both these issues. So it gives you all the refined data, or what we call engineering KPIs, right? And these very refined information that are used in machine learning. So this way you have information also on why and what has gone wrong, right? Or what will go wrong, rather, if you're talking about prediction. That's one aspect. A second aspect is you avoid false positives, because then all the additional data that is required for machine learning to do prediction, that is produced here. So this is how digital twin sits as a central component in overall predictive maintenance picture. Does it answer
You
your
spoke, yeah, definitely, Ankit. So a follow-up question on this is that you spoke about product as a service. Now, how
Mhm.
can digital twin help us turn a product into a service?
Yeah. Okay, perfect. So now let's take an example of so this I did not include in my presentation today. So this is for a compressor company that we are working with, based out of Germany. So they build a lot of compressors, right? That was their traditional business. So they would sell compressors, but now they were looking at if they could, instead of selling compressors, if they could directly sell compressed air as a service to their customer. And then customers typically are in oil and gas industry, mining industry, and also in process industry, right? Who use compressed air, who need that compressed air. So now they are delivering compressed air as a service. But of course, in order to do that, right, they still need to have a plant at this compressed air plant at customer site. But customer is not owning that plant. That plant is still owned by the OEM, by the compressor manufacturer. But they're only but the operator is only paying for the amount of compressed air that they are using, right? And in order to, but again, that could be, and that operator could use the asset in really, different way than it is meant to be. So in order to do a good monitoring of your or let's say, in order to charge the customer the right way, you would need, that digital twin, so that you can monitor that, how customer is using that compressed air, how is that affecting your asset health, or rather compressor health, right? So that is one example. And second example is that crane example, right? So also a lot of crane manufacturers are looking into solutions where, they are not selling the crane itself, but they are renting out the crane basically. So then they are leveraging product as a service, where operator would pay either based on how many hours they have used the crane for, or they would rent it out for a month, let's say, right? But irrespective of whichever scenario an operator is, renting out the crane for, as an OEM who is leveraging that way to do it, right? You'd still need to do a very good monitoring, right? So for instance, if crane is meant to build 100 kilos, right? And if operator is lifting 150 kilos every time, so then the wear and tear of your crane will be much faster. And how do you monitor that, right? And the only way you can monitor it by having this, real-time virtual twin or digital twin technology, where, depending on your uh, per, depending on your asset, that, if it's operated the right way, this is how my wear and tear would be. But since operator is not operating the right way, this is how wear and tear is, right? And then they can charge the operator accordingly. So this is how you can leverage product as a service via digital twins.
Ankit, if you allow, can I add something on that?
Yes, please go ahead.
Please go ahead.
Okay. Even in terms of, like, one aspect is like, okay, you can charge the operator. The second aspect, what Ankit already explained, is like, okay, when we have the digital twins, we have insights and information which we were previously not having, right? So now when is the asset likely to break, right? That is one of the things, right? So when to service that asset, right? And that is the insights, and that will help you to ensure the uptime of that asset, because that's where one of the models is like, okay, you're charging product as a service, but you need to ensure that the product is up and running. So this is where digital twin actually helps, in addition to what Ankit already mentioned.
Okay, thanks. Thanks for that. Any other questions from anybody? So another question that has come into the chat on a one-to-one is how. So we have been, in earlier this thing we have been talking about intelligent assets. which means the production assets. And now we are talking about intelligent products. What he's asking is, how are these two connected? Is there a connection between them, or these are two separate tracks that run parallelly?
No, not at all, rather. So I would say when we talk about intelligence in technology, right? So everything is connected, and this is how, as Sir mentioned earlier, right? If I may go back to point, right, and that slide, how we enable digital thread, right? So basically, let me quickly go here, yeah. So when we talk about this overall intelligence, right, everything is connected. So basically, now if you talk about intelligent products, so as an OEM, you are building intelligent products, right? So basically you're designing, you're collaborating with different parties, you are installing, and then you are selling it to your operator. And now operator is operating that asset in a smarter way. And then as I showed, there are different ways to do it, right? So one of them to do it is via digital twins based on the insights, and that digital twin is coming from OEM, right, as a digital product, for instance. And then that's one example of, and of course digital twin could also come from other, you could develop it yourself if you don't want to buy from OEM. Really, that does not matter. But at the end of the day, and then once you are operating your asset, you're maintaining it, then for instance, if you need servicing, right, you might also have some sort of agreement with OEM that they take care of the servicing, or you could generate service yourself, or how your asset is performing. You will always give feedback back to your OEM, so that they can improve the design for the next time, right? Or they can improve your product, basically. So this is how intelligent product and intelligent asset management are connected. So as an OEM, you are building up intelligent product, and as an operator, you are operating those products in an intelligent way. So what we call is intelligent asset management. So everything is linked.
Okay, thanks. Thanks for that answer and the other answers. Again, we'll wait for anybody else who needs to ask a question.
Mm-hmm.
Okay, I guess there are no more questions. Okay, there is another question that is coming. Please highlight in brief integration and interoperability between SAP and Siemens, as mentioned in one of your slides. This is
Yes.
from Mr. Dhanraj Shakare.
Yes, of course. So then let me just quickly jump into that specific slide of Siemens. And yeah, since we did not have time today, so I ran over time doing the use cases, so I did not have time to talk about it. But yeah, so basically how we integrate is with Siemens is that is via Teamcenter. So we have, and for instance, this is so let's say if you're using Siemens Teamcenter, right, PLM Teamcenter, and then if you want to bring all that data from Teamcenter to SAP's ERP system, so then we have built up an integration with S4. So now, all that data from Teamcenter can directly be brought to our S4 system via integration that we have built, and this is how we integrate with Siemens. And this, so that the specific integration piece between PLM and Teamcenter, Siemens Teamcenter and SAP's S4, that as of today is only available on-prem, but I think by the end of the year it will also be available on cloud.
Okay, thank you for that answer. Mukesh,
yeah.
Any other questions?
Can you hear me?
Yeah.
Hi, Mukesh.
Hi. So I'm sorry, I had to step out for a couple of minutes for something. So thank you so much, everyone, for your time, insights. I have one question. I do not know whether this was asked and answered before when I was stepped out. The question is the following, which is there is a whole suite of possibility when you are able to provide your product, not just as a product, but as a service. There is this entire concept of mobility as a service. There is a concept of hot air as a service rather than boilers. There is the service of mileage as a service rather than selling a vehicle. So how does this entire concept can be realized using what you're trying to do by the technology that you're talking about?
This is exactly, I think we talked about, right? I think someone
Oh,
else
you already
also asked
spoke
that.
about, okay.
Seems,
Okay.
but I can repeat,
Sorry.
Mukesh, no problem.
No,
No
it's
problem.
okay. If it was covered, that's okay. No problem. I just
So
wanted
I
to make sure that
gave example of a compressed air station. So similar to boiler. So basically, one of the customer is not selling compressors anymore; they're selling compressed air. So and how they're achieving it was also exactly the same case I talked about.
Okay. Okay. And so one of the questions that also comes in for me is, is this only relevant for heavy machinery or heavy big assets industry, or can it also be deployed in terms of consumer grade CPG kind of situations as well?
Yes, absolutely. So, so today since the theme was this, in this intelligent, how it goes intelligent, maintenance, but we also have a lot of customers in CPG and also in chemical and process industry as well, where they are, using specific EPD technology in their R&D and define phase in order to improve the R&D process. So specifically, let me just quickly go into so then they are specifically focusing on these aspects. So that is supplier collaboration, specification collaboration, product validation, document collaboration. So all of these aspects is something, where CPG industry is using our solution. And also, so that is like the R&D aspect. And anyway, in order to produce all of those products, right, you have some sort of assets, some machines that are producing those assets, right? It could be anything. And then we talk about the maintenance aspect. So then for those industry, if we talk about from maintenance aspect, then we have to think of maintenance of those assets. So that could, the assets those maintenance assets could be as simple as a motor, right? It doesn't need to be very heavy. We have customers doing it for as simple as a motor, but also at the same time as big as wind turbine, for example. But and in the R&D phase, they are typically using it for these specific pieces of the business process. That is collaboration, R&D, requirements engineering, product validation, etc. And when it comes to maintenance, it really does not matter if the asset is big or small. We can cover up to small also and also heavy assets.
And
This
Mukesh,
does not.
to your question on the okay, just another part or another aspect to this is, yes, we do look at the critical assets. That's the, I would say that's the positioning, but it also depends on what is the ROI, right? In terms of okay, you cannot, whether the customer wants to uh, monitor their small asset, right? It depends how critical that is, and if the asset fails, right, what is the opportunity cost for that? So that is one thing, and that the customer has to evaluate. When we talk about digital twins, we are only looking at very critical assets, okay, take an example of oil and gas. If the oil and gas plant shut down for a day, there are millions and millions of revenue loss for them on a daily basis. So that's the customer who has to decide, okay, whether this asset is critical for them. For the, I would say, the process industries, digital twin story only fits in the maintenance aspects, like Ankit mentioned. For the process industry, for the discrete industry, it could go into their assets as well, depending what they want to look at. Mukesh, you're on mute if you're speaking.
Oh, I'm sorry. Even after 2.5 years of doing this, your on mute still seems to be the most used term on Zoom or Teams calls. Sorry about that. I said if there are no further questions, I think I'm done with my questions. I would like to thank the presenters, Ankit, Saurabh, and team for the entire insights. And I know it was well received. Vipin, would you like to close out the session?
Maybe one point before we close from our side. Thanks everyone for joining this. Just in the interest of the time, we just pulled out I would say a handful of the use cases, but we have use cases across all industries, whether it's process or discrete. So if you are interested to know more, just feel free to just ping us, email us, and we can have those one-on-one conversations. Thank you. Over to you, Vipin.
Yeah, so I wish to thank everybody who has participated in this webinar. And like we have mentioned and we keep mentioning, if there is anything that you want on more information on any of these tracks, happy to connect with you offline. So thank you very much for your time.
Thank you for having me.
So the sessions are recorded and will be available as part of a YouTube playlist. You can download and watch them. We will also share the slides. So thank you so much for your time and take care. Bye.
Thank you. Bye.
Thank you, everyone. Bye.
Yeah, I finished it. Yeah.